Some objects give off light. They emit it. Some objects reflect light, and so we can see it. But what about those objects that neither give off light nor reflect light? Well, those objects are black, like this infrared camera. Now, black objects can give off light, but in order for them to do so, they must first get really hot. What I'm going to do today is talk about black body radiation, the kind of light that can be emitted from an object that ordinarily is black, but heated to a temperature where it starts to give off some light. And I'm going to do it by heating up this cube of iron. Now, strictly speaking, this cube of iron is not black, but it's close enough. The definition of a black body emitter is an object that absorbs all the radiation that falls upon it. It's black. We're going to heat this up under a Bunsen burner, and we're going to watch it through the infrared camera. I'm going to light the Bunsen burner now, and I want you to watch what happens to the screen. What I'm going to do is I'm going to get this on a nice hot flame. Just move the block so it is right over the right space, and we're going to watch it start to get hot. So what you can now see, now that the temperature is really high, is that the cube is now glowing with visible red light. But as it got hotter, it has now become red hot. You can see the block continues to glow with its own light emission way after the flame has been switched off. What I would see is that as it starts to fade, that the cube is glowing in a huge amount of infrared and also giving off red light. So is it possible for us to see white hot? It is, but there's a bit of a trick involved. We can't do it just with methane gas. If we had an oxyacetylene torch, then maybe we could do it. But instead, what I can use is a chemical reaction. The combustion of magnesium, or the oxidation of magnesium as it could be called, is something that produces a heat so high that the light that is given off is white, that it is a white hot reaction. Now, this is something that you shouldn't look at with your eyes unless you have glass. So here I have my glasses and my goggles, but it's quite safe to look at with those things. It's just extremely bright. This is something that is both bright and really, really hot, and so as a consequence, it's going to go white hot. I have my eyes shut because I don't want to see it. But here we go, a white hot burning magnesium ribbon. Did you see it? Well, that is hotter than that, and you could see that the colour had changed and also the intensity had changed. There was more light being given off because it was hotter, and that light was no longer red but white. Now we need to look at this in more detail. This is a chart of black body radiation, and some people find it really mysterious, like it's difficult to understand what it displays. Well, it's quite simple really. It looks at what colour of light is given off by a hot object and how much light. You can see on the y-axis it has the intensity. With more light, a brighter light, going to be higher on this graph than at the bottom. And on the x-axis we have wavelength, getting longer to this side here. In fact, if we look at this here, the rainbow in the middle is the section of the electromagnetic spectrum that we can see with our eyes, with 700 nanometers just here, 700 nanometers, and about 350 to 400 nanometers just here. This part of the graph is infrared. This part is ultraviolet, and this part visible light. Now what happens when we take a naturally black object and start to heat it up? Well, at a particular temperature, what we will find is that that object is giving out many different wavelengths of light. It doesn't give out just one wavelength of light. All of the different atoms in slightly different situations are all capable of releasing some of their thermal energy in the form of light, and some of them have slightly more thermal energy, some of them have slightly less. And this creates a distribution of possible wavelengths of light that a hot object can give off. So to start with, an object might give off a small peak of light in the infrared part of the spectrum. Now, this is an object that is basically about 200 Kelvin. No, not 200 Kelvin, because that's colder than room temperature. Let's go with, I don't know, let's go with 1000 Kelvin. Now, if you're unsure what Kelvin means, if you have not yet done the part of this course that involves Kelvin, consider it that this is about 1273 degrees Celsius. It's just a very, very hot temperature. Too hot to touch, but at this point, it is only giving off wavelengths of light in the infrared part of the spectrum. So the thermal imaging camera can indeed see it, but your eyes and mine cannot. Maybe we could feel it. But what happens if we continue to heat it more? And what happens is the peak shifts to the left and is slightly higher. And so here you can see the peak of this. So the sort of average colour has gone to more energetic wavelengths, but all of this infrared still, of which there is now more, is still invisible to our eyes. But what has happened is a small amount of those atoms are giving off wavelengths of light in the visible part of the spectrum. So this here is a temperature of, let's have a look, let's say 2000 Kelvin. And at this kind of temperature, what we can see is the object has begun to give off visible light. But look at the colours of visible light. Mostly red, and only a tiny bit of the other two prime colours for light, which is green and blue. So with the dominance of the red, this is red hot. Let's do it with a red chalk. This is a red hot object. But then what happens if we turn the temperature up yet further? So it is brighter, and the graph looks more like this. This is something, say, about 6,000 Kelvin, 6,273 Celsius. But just look what it's doing. First of all, it's much brighter. This is like the magnesium ribbon. And what is going on here is you can see it's giving off a huge amount of infrared. It's even giving off some ultraviolet. But look at what it's doing in the visible part of the spectrum. It is giving off some red and some green and some blue in equal measure. Red plus green plus blue equals white light. And so this is white hot. Now something else that is white hot, that we don't see every day here, but is around sometimes, is the sun. The sun has a surface temperature of about 6,000 Kelvin. Now that means that it's giving off almost an equal amount of red, green and blue, and so it appears white to our eyes. The sun itself is a brilliant black body emitter. it is an object that if it cooled down, it would be black. But it is glowing with light because it is so hot. An interesting question is what happens after this? Well, an object that is hotter still will look like this. And you can see that there's more blue than red. This is an object that is getting on to about 15,000 Kelvin. It actually becomes, believe it or not, blue hot. And because this temperature scale goes from about 2000 Kelvin to about 1500 Kelvin, then it actually matches quite nicely with the temperature range that we see in stars. When you look out into the night sky, don't be fooled into thinking that all of those stars are the same colour, because they're not. The big old dying red giants are much cooler objects than the gloriously new and emitting young stars like stars like Rigel and those nice blue stars. If you look at the night sky, you'll see that some of them are blue, some of them are white, and some of them are red. One final thing is what happens after this if it's hotter still. Well, what happens after this is the peak is way over here in the ultraviolet. And so what we start to see is a smaller contribution in the visible part of the spectrum and a larger contribution in the ultraviolet part of the spectrum. White dwarf stars, the dying remains of a dead sun, can be so hot when they first form up to 100,000 Kelvin, they give off nearly all of their light in the ultraviolet, and that is why it's so difficult to see them with an ordinary telescope. And we would have to use a telescope that looks at ultraviolet from space. So here we have it, the black body spectrum. This explains to us why a hot object gives off different colours, why that colour changes, and why it gets brighter when it is in fact hot. On that last point, why does it get brighter when it is hotter? And that is just because more of those atoms are giving off some of that thermal energy in the form of light. With a good explanation, this is really easily understandable, and it explains so much that we see around us, from something in a fire glowing red to the stars in the night sky.